So, as I showed you guys in the PowerPoint, we can actually find the efficiency of the solar cell by conducting current voltage measurements of the cell under illumination. Now, here is the equation to find the efficiency, and here's the curve that's generated when you take the current voltage measurements. Now, notice though that the curve doesn't exactly give us the values that we need in order to find the efficiency. We have the values for the open circuit voltage and we also have the values for the short circuit current, but this actually doesn't give us the values for the maximum current and the maximum voltage, which is what the equation for efficiency is asking us. So we introduce what's called the fill factor, and this is the equation for it. Now, the fill factor is essentially a measurement of the quality of the solar cell, whose value can be anywhere between from 0 to 1. And if you actually got a value for a fill factor that was 1, you would kind of get a graph that would sort of look like this, kind of rectangular. But because this actually isn't possible, you usually end up with a sort of a curve. Now, the reason why the fill factor is so advantageous is because we can actually rearrange the equation by solving for the maximum current and the maximum voltage. Now, if we solve this equation for the product of the current times the voltage, you get the fill factor times the short circuit current times the open circuit voltage, which is equal to the product of the maximum current times the maximum voltage. Now, if you go back to your original efficiency equation, which sort of looks like this, you can actually plug this in place of the maximum current and the maximum voltage, so you rearrange the equation and you end up getting this. And because this is actually in terms of the short circuit current and the open circuit voltage, which is what we get from the current voltage curve that we get from those measurements, we can actually find the efficiency. So now I'm going to go over how we're going to be getting all these different information from the actual curve. Now, if you look at the graph, right, you've got the value for the short circuit current and you've also got the value for the open circuit voltage. So that means that you have the values for these two variables here. Now, the problem is that we don't have the values for P in, right, and the fill factor. So now, in order to find P in, here's the equation. Right, so this equation here, as you can see, really, we already kind of have the value for this. All you have to do is find the surface area of the cell. And the way that you do that is that you find the length and the width of the rectangular area of the working part of the cell, and then you multiply it by this value. And this value is equal to 1 sun, and the solar simulator that we're using actually is going to be giving off in a light intensity that's equal to 1 sun. So we can automatically assume that the light intensity will be 1000 watts divided by meters squared. So then you just find the surface area of the cell and then you plug it into P in, which means that we actually also have already the value for P in, the power. So the thing is, however, is that we don't have the value for the fill factor. So I'm going to show you guys how you guys are going to figure that out from the actual graph. So as you can see here, I actually sort of rearranged the fill factor equation, and then I also drew out a drawing here. Now, if you look at the blue curve, that's your original current voltage curve. Now, what I did was that, now notice here at the equation, right? You've got P max, which is the maximum power of the cell, divided by the theoretical power of the cell. So if you look over here, right, I have the open circuit voltage and then the short circuit current. Now, if you were to sort of draw a dashed line to form a square, that would give you the theoretical power. Now, because solar cells cannot be 100% efficient, we end up getting the curve. So, which means that the maximum power is actually not up here, but it's somewhere down here along this side of the curve. The question is how we find it, right? And when you find the maximum power, you're able to find VMP, which stands for voltage at the maximum power, and then you're able to find IMP, which is the current at the maximum power, which also stands in for the maximum current and the maximum voltage. If you guys remember, the original equation had maximum current times maximum voltage. These mean the exact same thing, except in this case, because we're finding them in terms of the maximum power, you end up with IMP and VMP. Now, in order to be able to find these two different variables, though, we have to find P max. And now the way that we find actual P max is by multiplying all the voltage values that we got times the current values. And the way that we do it is you multiply the X and Y values together. And the reason why we do this is because power is actually current times voltage. So if we do this with all the values that we have along this curve, we will actually get the values for power. And what ends up happening is that you sort of get a curve that kind of looks like this. Now notice, right, that I just drew this green curve. So what I did, right, was that I took all my voltage values and I multiplied them by the current values that I got, and then I ended up getting the different values for power, and then I graphed the power values on here, and I had on the x-axis the voltage values. So what you do, right, you have power, you put it on the y-axis, and then you have voltage and you leave it on the x-axis. And if you notice, this graph actually has a maximum up here. And you find that maximum, and that's actually your P max, your maximum power. So once you're able to find that, then what you can do is that you can find the X value where the maximum power is at, and then you end up getting the voltage at the maximum power. And then if you go back, so I still have the original graph on here, you can then also find the Y value for the maximum power at the current. And the way that you could also do this, instead of just going on your original current voltage graph and put it in graphing P max on there, where the X value for the voltage is, and then sort of trying to figure out the Y value, the other way that you could do this is by simply plugging in the value for the voltage and then the value for power into this equation and solving for the current, and then you would also get this value. So there are two ways you could do this. It doesn't matter which way you do it, but this way would probably be a bit more accurate just because it's actually in the equation, and if you try to do it in the graph, it would be a bit, you would just be estimating. Right, so now if you notice, we have the current, right, at the maximum power, and we've also got the voltage at the maximum power, which means that we can actually find the fill factor and then plug this into our efficiency equation, which I wrote down here, right? You can plug it into this equation. And since we already have the values for the open circuit current and the short circuit voltage, and we also have the value for Pn, then we can just plug in the fill factor here. And then that's how you find the efficiency. So just a bit of trivia here. I'm going to actually show you guys why this equation is able to work. So if you think about it, when you calculate the efficiency, the units for the short circuit current are in amps, right? And then the units for voltage are in volts. And fill factor actually doesn't have a unit because remember, it's just a ratio. And then for power, the units for power are in watts. And so when you multiply, remember, current times voltage, you get power. So if you have amperes times voltage, you get watts over watts, which would, of course, equal to a unitless efficiency. Now, the last thing I wanted to talk about was how to find the shunt and series resistance, right? So those are two different resistances, and you can actually find them from the current voltage curve, which I have here in blue, right? That's the one that you find under illumination. Now, you guys will also be doing a current voltage curve that will be conducted in the dark without illumination, and the curve will kind of look like this. They essentially should kind of look the same. And usually what happens is that this curve, this green one, what happens is that as you increase the light intensity, this curve actually ends up shifting up and up and up until you get to this blue curve up here. But here I have both of them shown, that way you guys know what they look like. So, in order to find the shunt resistance, what you're going to do is that you're going to find the inverse slope at the short circuit current. So what you do is you sort of find the inverse slope at this point, and then that gives you an estimate of what the shunt resistance is. And then in order to find the series resistance, what you do is you find the inverse slope at the open circuit current, and that's going to give you the series resistance. Now, the last thing I wanted to tell you guys is that you can actually also estimate the shunt resistance from this dark current curve, the one that the current voltage curve that you guys took will be taking under no illumination. And what you essentially do is that on this curve, sort of like the linear part of it, what you do is that you find the inverse slope of that, and that's going to give you the shunt resistance. Now, I just want to mention this. These are just estimates of what they are because this graph right here was done under no illumination and this one was done under illumination. You might get slightly different values between these two different estimates, but it just depends on how well your cell works under illumination or if there's anything wrong with it. But that pretty much concludes all the sort of things that you guys kind of need to know in order to be able to understand why we're able to do these measurements and figure out all these different things.